Brad Williams, Frugal Finance, computing Black-Scholes option pricing. In this section, we show how to compute Black-Scholes option prices. Assume that a stock price at 100x and the risk-free interest rate is 6% R. A call option on the stock has an exercise price of 100 S and expires in 1 year T. Fill in the blanks. The standard deviation R squared of the stock return is 0.1 per year. We compute the value of DISA 1 and DISA 2 as follows. We're just going to follow this information. We're going to fill in the variables and we're going to come up with this. DISA 1 is equal to 0.65 right here. You want to do the number crunching, there it is. Then DISA 2 is equal to DISA 1, 0.65, minus, it looks like the variance, DISA 1 minus DISA 2, which will be squared. And DISA 2 is equal, so we're going to look at here. This looks like 0.65 minus 0.1 times 1, which is 0.55. Next, we find the cumulative normal values associated with D1 and D2. You probably can cheat. I'm going to talk about some graphs and what have you. I didn't attach them. So if you want them, let me know and I'll prepare them. They're not that important. The reason being is because we're using this norm distribution by Excel. Just a huge time saver. These numbers are the probability of a normally distributed variable with a zero mean and a standard deviation of 1 having a value equal to or less than the DISA 1 or DISA 2 term we are using. Figure 13a shows a graph of a normally distributed variable with a zero mean and standard deviation of 1. It shows the values of DISA 1 and DISA 2 for our example. For illustration, we focus on DISA 1, which equals 0.65. And finding in DISA 1, we want to know which portion of the area under the curve lies to the left of 0.65. This is the value of n DISA 1 to the left. Clearly, the value we seek is larger than 0.5 because DISA 1 is above the mean of 0. We can find the exact value by consulting a table of the cumulative normal distribution for this variable or use norm distribution function. For a value of 0.65, we find our probability on the interior. N65 is equal to 0.742. Similarly, N DISA 2 is equal to 788. We now have the following. Normal distribution 0.7422, normal distribution 7.98. Negative R times T at T is a rate of 6% with 1 year to maturity equals EXP 0.06 times 1 equals 0.9418. C is equal S times N. Plug that in and we have 7465. We use these values for our sample because they parallel the values from our first binomial example. There, we also assume that the stock traded for 100 and that the risk-free rate was 6%. We used an up factor of 10% and a down factor of negative 10%. Adding these values in a single period binomial model, we determined that a call should be priced at 755. The results are very similar. If we use more periods in the binomial model and utilize up and down factors aligned with a log normal distribution of stock returns, the binomial model will gradually move towards the price predicted by the Black-Scholes model. What does that mean? Do you want to use the binomial model? Probably not. You can see right there, that's a big change. In this example, we talked down the binomial, but as a percentage, 755 to 746, that's significant. That's a huge difference. If you're experienced and perhaps your binomial model matches Black-Scholes, then good for you. Otherwise, if the market recognizes Black-Scholes as a better instrument, then clearly that's the way to go. Brad Williams, Frugal Finance. Thanks for watching.